Now let's go to Memristor, right? We are done with the power device. We have very tight schedule. I give you a feeling. I hope that you can keep paying attention. It's very hot now. You definitely see from the news every day about this ultra band gap, ultra wide band gap, and wide band gap. If you go EE times, right? Now we talk about another thing that you also see every day, Memristor, right? So these are the paper I uploaded. You can take a look. Memristor is what, right? It's explored by trial in a scientist, I forgot who, where, maybe AT&T, Bell Lab, or whatever. He said we miss a circuit element, right? We have transistor, resistor, capacitor, inductor, and then he said, hey, we actually need another thing called memristor, that the resistance depends on the history of the applied voltage. That's the main point. All the memristor, the main characteristic is its resistance depends on history. Whatever depends on history, what does it mean? It means it has memory, just like us, right? If we forget about everything, what happened before, then it means we don't have memory. If our action depends on what happened before, whether we really put a memory there or not, we do have a memory, because what happened in the past is affecting what we are doing now, right? Very philosophical question. Going back, remember in the lecture 3, I talked about the memory wall. Now our CPU gets so fast, but our memory is so dumb, okay? So slow, right? And that's why NVIDIA is so successful, because they have a special architecture for GPU, and also they try to bring the memory closer to their GPU, hybrid memory, right? HBM, high bandwidth memory. You see, there's a big difference, right? You have a very smart brain, but you get information very slow because it takes a long time to transfer the data to you. So there's a memory wall, a speed gap. We also talk about Stanford's, too fast. We also talk about if we can solve it, we can solve many problems, right? What do we want? Memory need to have low energy also, not just high speed, because memory is so important. Your brain have trillions of connections, hundreds of billions of neurons. I probably mess up the number by a few orders of magnitude, but it is in the lower side. It should be only more. But your brain only consumes 20 watts of power, means 20 joule per second. Okay? The light bulb, even the energy saving one in your living room, is already 8 or 10, right? You are doing such a smart thing, controlling a body, thinking, and you only consume 20 watts. If we want to have something like our brain, it cannot be just fast. It needs to be low energy consumption. You need to be close to the CPU. This is because we want to make it fast and also reduce the energy consumption. Transportation of data is very expensive. This is very intuitive, right? If you need to commute to San Francisco every day, it's very expensive. Think about all the San Francisco people need to go to San Jose, and San Jose people need to go to San Francisco every day. A lot of energy required, right? So we need to make them close. So there are different types of memory we're going to discuss in this class: resistive memory, spin-torque transfer memory, phase change memory. They all have their characteristic. They are fast, small programming voltage. Low programming voltage means that low energy again, right? If you need high voltage, it means high energy, okay? Another characteristic is that they can be processed at low temperature, so they can integrate to logic. And this idea, of course, not just from Stanford, but they had a very grand plan at that time. I think they start really realizing some of their plan. But basically, it is we have all the advanced logic, 2D, two-dimensional facts. We did not discuss in this class, 2D material. right? But you can just treat them as nanowire or nanochip, whatever, carbon nanochip, do the computation. On top of it, we just deposit the spin torque transfer memory very fast, faster than the, as fast as the SRAM, but they are so close. They are just on top of the transistor, maybe even closer than SRAM to the CPU, because after all, although SRAM is L1 cache is on CPU, but again, they need to transport laterally, but this is just on top of it. And also, this can have much larger capacity. You can do 3D integration. And then next layer, you can do resistive memory. A little bit slower, but a lot. Why I'm going to show you is really a lot, right? And then they say that they are going to have 37 times energy consumption reduction and 23 times speed up at the same time. I don't know if I remember it correctly, but doesn't matter, right? So I think they are at the same time. Remember, they talk about 1,000 time improved in figures of merit. Okay, so both energy and speed need to speed up by one. Their products need to be 1,000 times. Right? How do we do that? You can say that's a hype, but this is what's going on now, right? All the device research central around this, if they were not doing the logic, because this is the most important thing. Okay, just think about this COVID-19. Micron, Samsung, what else? Micron, Samsung, Western Digital, the former SanDisk, right? Their revenue actually increased a lot because memory demand actually increased a lot. Many people buy electronics, need a lot of memory. And memory can only be more important in the future, right? So in the past, memory is very boring. When I was in my PhD degree, I see the people working on memory. I feel they're working on something very boring, not as excited as doing the transistor, but they are more important than transistor nowadays, actually. Okay. So we say we're going to do Memristor. Okay. So what is Memristor again? The missing element proposed by Chow, right? Now, they are not just memory. The most important thing is that they can be used for the neuromorphic computing. We are going to cover later, right? We don't discuss now. Now just treat it as a memory, storing 0 and 1, okay? And what is the requirement of the memory due to the memory wall I mentioned already, right? You need high density, low power, right? Maybe I write it down, not higher power, but low power. Another is endurance. You need to write it many times, right? But this really depends, right? How often do you rewrite the same location of your USB? If you use it to store your photo, maybe you only rewrite it every half years, right? You don't take so many photos, right? You probably overall, before you lose your memory state, you only rewrite it for 10 times at most, right? So for some memory, it's okay if their endurance is not that good. But if we're talking about to replace the SRAM with STT-RAM, it's talking about what? 1 gigahertz. If you keep trying writing them 1 billion times every second, that is a lot of endurance that you need to have. Okay, so market purpose is also important. Okay. Now, people demonstrated this 10 to the power 12, that is 1 trillion times of cycle, sub 1 nanosecond switch, sub 1 picosecond Joule switch, this voltage, 10 years retention, 8 nanometer dimension. Wow, that's perfect. But I just put them together and then I warn you, I pick up from different experiment and materials. Okay. There's no such material or memory yet can do all of this, right? If you can do this, you are going to be very rich tomorrow, richer than Bill Gates, because this can replace every memory in this world, right? So, but we just want to learn what it is, okay? So that's why I'm trying to say we are greedy. We want to have low power, high density, closer to CPU, high speed, and low cost. Okay. Any questions? If no, let's just look at one of them first. ReRAM, right? What is ReRAM? ReRAM stands for resistive memory, or RAM. RAM is random access memory, just a regular RAM, right? Why? What's so special about this? For this type of, what we call this, right? I forgot to tell you. All this thing, right? We actually, if you go out, right, conference or whatever, they have a name. They call emerging memory. Okay? They are still emerging. They are not new yet. But usually they are long volatile. This is the main point. What is the meaning of long volatile? Can someone tell me? What's the meaning of long volatile memory?
It retains its state after power off.
Yeah, this is important. Yeah, your SRAM is fast, consume a lot of memory. Not just this, if I turn it off, all the content are gone. STT-RAM keep the content, right? So that's why you can have a very fast restart, right? I'm not talking about computer restart. Computer restart is due to the flash memory, but you can say, why is that? Because in order to save, I mentioned this before also, to save the energy of your CPU, you actually can turn off a block, turn on a block anytime when you don't use it. If for SRAM to turn off this block involving the SRAM, you need to copy the data to outside first, and then you turn it off. Man, it consumes so much memory to copy the data, so much energy to copy the data, right? Now, for this one, I just turn it off right away. And then I want to start, turn it on. So it's so easy to decide this so-called power gating, right? Power gating, we kind of discuss in EE224, but we don't discuss here because this is not circuit, right? But with this one, you make the circuit design so easy. So I hope you to memorize this. When we talk about this emergent memory, they are all, most of them, right? I cannot think of anyone that is not long volatile. Very useful, not just fast, long volatile, right? And in the past, we